everything I will say today is joint work with Jason Lunn, who is a very clever guy, currently a postdoc at the University of Oxford. So I will start by reminding you of a couple basic theorems from combinatorics, starting with Sperner's theorem from 1928, which just says something about the largest antichain in the Boolean lattice. The way I will phrase it is as follows. It says that if F is a family in the Boolean lattice, and it doesn't contain a chain of length 2, so it's 2-chain free, then the size of F is bounded by the size of the largest layer of the Boolean lattice. So just a reminder, Boolean lattice is just a collection of subsets of an n-element set ordered by inclusion. A chain of length 2 is simply two sets A and B, with one of them being a subset of the other one. And the layers of the Boolean lattice are just collections of sets that have all the same size. So the largest layer happens to be the one containing sets of size n over 2, and the size of the largest layer is n choose n over 2. So here's a picture of what's going on. Here's the Boolean lattice, with the empty set being at the bottom, the full set being at the top. We want to pick many elements of the Boolean lattice, and I want to pick many subsets of an element set without picking two sets so that one of them is contained in the other one. Sperner's theorem says the best thing we can do is take a layer, namely take the largest layer. So we look at the layers of the Boolean lattice. We notice that the middle layer happens to be the biggest one. So we take it, and Sperner's theorem says that this is the best thing we can do. Now, Sperner's theorem is a cornerstone result of external combinatorics, and as such, it has a billion different generalizations. So the one I will use here is a generalization due to Erdos from 1945 that says something about not chains of length 2, but rather chains of length k for some k larger than 2. So Erdos' theorem says that if you have a family that's a subset of the Boolean lattice that doesn't contain a chain of length k, then the size of the family is bounded not by the largest layer, but by the size of the union of the k-1 largest layers. So here, a chain of length k just means k sets, A1, subset A2, subset AK. So k sets totally ordered under inclusion. So here's again a picture. That's the Boolean lattice, empty set at the bottom, full set at the top. We want to pick many elements of this Boolean lattice so that we don't create k sets that are totally ordered like this. And Erdos' theorem just says, take the largest layer, then take the second largest layer, third largest layer, and so on. Keep on taking layers until you've hit k-1 layers, and then you stop. This family doesn't contain a chain of length k, and this is the best thing you can do. There is a different generalization of Sperner's theorem that I also want to mention, because I will use it in my talk later, and it started with a question of Erdos and Kleitman. So Erdos and Kleitman said the following: we know what happens with families whose size is equal to n choose n over 2. They need not contain any comparable pairs. But what can we say about families that are larger than that? At least how many comparable pairs must they contain? In other words, if I give you a number m, how can you find a family in the Boolean lattice of size m which has the fewest number of comparable pairs? So which family in the Boolean lattice of size m has the fewest two chains in it? So this is what they asked, and before I tell you what the answer is, let's just try to guess what a natural construction or natural guess would be to this squaring question. So here's the Boolean lattice. Our task is to pick an element of the Boolean lattice so that we create as few chains of length 2 as possible. How should we do it? The very natural approach is to do kind of greedy strategy. We start by taking the full middle layer, which is good because we've taken many steps without creating a single chain of length 2 so far. And now we have to do something else. So if we pick the next element kind of very far from the middle layer, that's bad because this element is a huge shadow down here in the middle layer, which means if you take this set, you've created many comparable pairs. That's not good. So instead, you want to take an element that's very close to the middle layer, for example, in here. So you continue your process by taking this layer. And then you keep continuing. Then you take the next largest layer, and keep on taking the largest layers one by one until you finally end up with a family of size m, and then you stop. So notice that it doesn't matter what you do on this last partial layer that you don't fully fill up, because it doesn't matter which elements you've taken here, the number of comparable pairs or two chains you've created is going to be the same. And this is a very natural guess as to what the answer should be to this question. And indeed, this is exactly what Kleitman proved in 66. Kleitman proved if someone gives you a number m, and your task is to find a family of size m, which has the fewest possible number of two chains in it, then you should do exactly what I just showed you. Keep filling up the largest layers one by one until you hit a family of size m. So Kleitman proved to minimize two chains. I'm going to write take largest layers, but what I mean is really what we said here. Keep putting up the largest layers one by one until you run out of elements. So Kleitman's paper is very impressive for two separate reasons at least. First of all, the way he proved this is a magical compression proof. He defined several different compressions that work together beautifully and with which he managed to prove this statement. Another reason why this paper is so influential is because on the very last line of this paper, he mentions a conjecture that was open for over 50 years. And if you look at the year, you can kind of guess roughly when this conjecture was proved. Okay, so what was Kleitman's conjecture? Well, Kleitman said, I just told you how to minimize two chains. But what if your task is not to minimize the number of two chains, but rather minimize the number of chains of length 17 or something? How do you do? And Kleitman's conjecture is, you do the exact same thing. So conjecture, Kleitman, same paper. To minimize k chains for any k, you do the same thing as before, keep taking largest layers. So let me just very briefly tell you what the history of this problem is and how it's ended up being solved recently. So first observation is that if the size of the family you have to create is less than the size of the k-1 largest layers, then by taking largest layers you end up with a subset of the k-1 largest layers, and this contains 0 chains of length k, so this is trivial. Just very briefly, some recent history. Dove, Griggs, Kang, and Sereni in 2014 proved that the conjecture is true. So it's true if M is bounded by not k minus 1 largest layers, but the k largest layers. So the bound is one layer above the trivial bound. Then independently from them, a second group of authors, Dasgan and Sudakov, in 2015, independently from the first group of authors, proved that it's true if M is at most the k plus 1, the total size of the k plus 1 largest layers. So now we are 2 layers above the trivial bound. Then Vitioji Barog and 17, he proved that it's true asymptotically if n is bounded away from 2 to the n and n is sufficiently large. And very quickly afterwards, Wojtek Samotij found a way to actually make this proof work for all values of the parameters. So we proved the full conjecture. So now Kleitman's conjecture has become Samotij's theorem. So these are the 4 theorems that I wanted to mention. And this is what my talk will start with. I will start with these 4 theorems, start modifying them, and we'll see where this thing will take us. So I just want to put them up here, just for reference. We have Sperner that says if F is a subset of Boolean lattice, no 2-chain, then the size is at most the largest layer. We have Erdos, which says that if you have a Boolean lattice, no k-chain, then the size is at most the k minus 1 largest layers. And then we have 2 theorems that says something about how to minimize number of chains. We have Kleitman's theorem. If we want to minimize 2 chains, then we take largest layers one after the other, keep filling up the largest layers. And finally we have Samotij's theorem just over there that says the same thing is true for minimizing chains of length k. So I will start with these 4 theorems, and now let's start to slowly modify these theorems and see where this can get us. So the very first easy modification I want to do is just by observing that the Boolean lattice is just a collection of all subsets of an n-element set, and every subset of an n-element set can be identified with its characteristic vector. So the Boolean lattice can be identified in a very natural way with 0, 1 to the n. Right, so you just take a characteristic vector from its set, and that gives you an element of 0, 1 to the n. And the set 0, 1 is just a vertex set of z2. So this is just z2 to the n. So the Boolean lattice can be identified with a vertex set of z2 to the n. So what I can do is I can go here and replace the word Boolean lattice everywhere with z2 to the n. Right? So I haven't done anything so far. All I said was that 0, 1 is the vertex set of z2. So this is z2 to the n. So I can write z2 to the n everywhere here. If you have any questions, then let me know.
G to the end the power.
Yes, thank you. Right. Okay. And over there as well. Okay. So thank you. So that's actually a mistake here. So it should be Z2 to the n, which is, so this is, should be Z2 to the n. Z2 to the n is a cyclic group. This is not a cyclic group, so this was definitely wrong here. And over there I also wrote Z2 to the n everywhere, which is very stupid because unfortunately if I write Z2 to the n, then in a cyclic group I don't know what the word chain means. I don't know what the word layer means, so unfortunately these four theorems don't make any sense. Thank you very much for pointing out this mistake. Yeah, so this is very embarrassing. So just imagine yourself in my place. You're here trying to give a talk to this group full of brilliant postdocs and previous students and professors, and you make such an embarrassing mistake. Do you like double down and try to prove these four theorems, which is going to be hard because they don't make any sense, or do you apologize and say that you made a mistake and look stupid? It's a bad idea. So actually, let me tell you a story. It's a story about the most inspiring talk I've seen in my life, which was a talk given by John Conway, who visited us 7 or 8 years ago in Cambridge. So John Conway talked about infinite integer sequences, and he defined some kind of property on these infinite sequences. Some sequences had this property, they were called the good sequences, and some sequences did not have this property, they were called the bad sequences. And it wasn't clear where he was going with it, because the sum of two good sequences was sometimes a good sequence, sometimes a bad sequence. Sum of two bad sequences was sometimes good, sometimes bad. So it wasn't clear whether there's any structure to what he was saying. And at this point, John Conway said the most brilliant idea I've ever heard in my life. He said, let's assume that the good sequences form a vector space. Which was a ridiculously stupid thing to say, because even my first year undergrad linear algebra students know that vector spaces have to be closed under addition. The sum of two good sequences was usually not a good sequence. So what he said didn't make any sense. So then John Conway said, okay, what I said doesn't make any sense. So let's assume that this makes sense. If the good sequences form a vector space, then integer addition has to be defined differently. In particular, he kept on reasoning and logically reasoning, and the first theorem he proved that under this new kind of addition, you must have 1 plus 4 equals 7, and he kept going and going and going, and by the end of the talk, he managed to define this magical new kind of integer addition under which the good sequences indeed did form a vector space. It was absolutely brilliant and magical and genius talk. So I'm not claiming we'll ever be able to replicate the brilliance of John Conway. Here it's not going to happen, but we can try to do it on a small scale. Here I have four theorems that don't make any sense because I put the n in the wrong place. They don't make any sense because in cyclic group we don't know what chain means, we don't know what layer means. But let's assume that these four theorems make sense. Let's figure out what they could possibly mean. In order to do so, we need to find definitions for the word chain and for the word layer. And we need to find these definitions in such a way that these four theorems become true, and even more importantly, that it leads to some interesting mathematics. So that's our task. Let's get going. Let's start with the word layer. What could the word layer possibly mean in cyclic group Z2 to the n? Well, if you think back to the Boolean lattice, you know that the Boolean lattice consists of n plus 1 layers. So how nice would it be if we could find some kind of natural partition of Z2 to the n into n plus 1-ish layers in some natural way. And well, luckily for us, there exists a very natural partition of Z2 to the n into exactly n plus 1 sets, namely as follows. Let's say that the first layer is a set of all odd numbers, L2 will be all numbers that are 2 mod 4, L3 is all numbers that are 4 mod 8, and so on. This gives us exactly n plus 1 layers, each of them, except for the last one, half as big as the previous one. While in the Boolean lattice, we partition into layers according to the size of the sets. Now we are partitioning according to the largest power of 2 dividing the number. So I'm sure you would agree that this is a very natural way to partition z to the n into n plus 1 layers. So let's stick with this definition for the word layer. So we're halfway done. All we have to do is now figure out what the word chain should mean. And let's start with chain of length 2. So Sperner's theorem says that if you have a family that doesn't have a 2 chain, then the size of this family is the largest layer. So in particular, in our case, the theorem will say if we have a subset of z2 to the n with no something, whatever our analog for a 2 chain will be, then that the size of the family is at most the size of the largest layer, which happens to be R1, the set of all odd numbers. So the question is, what do I put in the blank space so that this theorem becomes true? And well, we can start trying a couple of things. Maybe a first natural thing to try is x and 2x, a number and its double. This looks like a 2-chainy kind of thing in the world of z2 to the n, so maybe this is the correct analog of chain of length 2. Unfortunately, this doesn't work because this inequality is not going to be true, because in particular L1 union L3 doesn't contain this kind of objects. It's x to x3. L1 is the set of all odd numbers, L3 is the set of all numbers from and 8. There is no number in this double ring. So if you think about it for a few more minutes, a natural try that you will eventually find is not x and 2x, but rather x, y, and x plus y. 2 numbers and their sum. And this is indeed something that if you write in there, it works. Not containing x, y, and x plus y just means that you have a sum-free set, and in the group z2 to the n, the largest sum-free set is indeed size 2 to the n minus 1. So this is good. Not only does x, y, x plus y fit in this box and make this theorem true, but something else also happens. In the case of Sperner's theorem, what we had was that the largest layer was actually an example of a maximal sized 2-chain free thing. And here the same thing happens. The largest layer, a set of all odd numbers, is actually a witness proving the sharpness of this analog of Sperner's theorem, which I will put now in quotes because it's not the original Sperner's theorem anymore. So not only is it true, but actually the largest layer is a witness for the sharpness. So we have 2 reasons to agree that we'll just write down the 2 chains in our new weird word will correspond to these triples that are called Schur triples. So Schur triple just means 2 numbers and their sum. So we're making good progress. We have defined layers, we've defined 2 chains. All we have to do is define longer chains. Just a very small digression here before I continue with the talk. This statement of finding largest sum-free sets in cyclic groups actually has a rich history. So I'm just going to write it here. So just a small digression. This is not part of the talk. So largest sum-free set in a cyclic group, z over nz. So the answer to this question depends on the prime factorization of this number n. And according to the prime factorization, the group is either type 1, 2, or 3 in some particular way. And for type 1 and 2, this was solved by Dyananda and Yap in 79, I think. And for type 3 groups, it was open for a very, very long time. And after incremental progress, there was a breakthrough paper by Green and Ruja in 2005 who completely answered the question for type 3 groups. And now this question is completely settled. But just by this weird route that we've taken, we accidentally worked into this area of some very, very difficult problems. But fortunately for us, we were in the case where the order of the group was power 2, so everything was easy. So now let's continue and let's try to figure out what the correct analog of chain of length 3 is. So in order to figure out what the 3 chain should correspond to, let's look at Erdős theorem. Erdős theorem in our world will say that if, so in Z2 to the n, the largest 3 chain free family, 3 chain I will replace by blank because I don't know what it is, has size, actually let's write is L1 union L2, because just like in Erdős's case, the largest k minus 1 layers are an example of a largest k chain free family. Here I would like to have the same thing happening. Question is, what do I put in the blank space? So just like before, let's try to guess a couple of things. Maybe we got lucky and we guessed the correct thing. So over there we had x, y, and x plus y. So maybe natural thing to write down is x, y, z, and there's some x plus y plus z. It's worth a shot, maybe this just works. Unfortunately, this doesn't work because if x is 1, y is 3, z is 5, then you get the set 1 through 5, and 1 plus 3 plus 5 is 9. This is actually all contained in the first layer. These are all odd numbers, so it's definitely contained in the first 2 layers. So if this is what the 3 chain means, then it's not true that the first 2 layers are 3 chain free. So this doesn't work. So maybe we should forbid something bigger. Let's make it harder to find these things. So instead of forbidding 3 numbers and their sum, let's go all out and forbid 3 numbers and all possible subset sums. So x plus y, x plus z, and x plus y plus z. This ought to work. This is a natural generalization of what a true triple is, contains as many elements as you could possibly squeeze in there. So if this doesn't work, then I don't know what we're going to do. Oh, unfortunately, this also doesn't work, because if x is 1, y is 5, and z is 9, then you can check that all the numbers will be 6, 10, 14, and 15. And this is actually contained in the first 2 layers. So that this also doesn't work.
Should be y plus z.
Yes, thank you. I have that here. Okay. Yeah, so 3 numbers in all possible subsystems. Okay, so there's a problem here. So what do you do if you cannot guess the correct answer to put in that space? So the observation here is that there is no reason why there really should be something that you can put in that space to make this theorem true. The only reason why we thought that something like this might be true is because we assume that mathematics is beautiful and this kind of connection between z2 to the n and z3 to the n must hold, and so there must be some kind of dictionary between these 2 rows. But there's absolutely no reason why that should be the case. In particular, when I was trying this, I tried hard to think of what to put in the blocks, but I just couldn't come up with anything. And there's really no reason why something should fit into the box. But before you completely give up, there's one last very desperate thing that you can try, which is the following. you can observe that no matter what kind of natural thing you write into that box, as long as it's something nice like this, the resulting statement can be phrased as a linear program. The good thing about linear programs is you can take an LP solver, just throw it at them, and it will spit out whether it's true or false for small values of n, and you can get a good guess whether it's likely to be a true statement or not. But you can do more than that. You can actually write a program that generates guesses. For each guess, it writes statement as a linear program, takes an LP solver, throws it at the statement, and spits out whether it's true or false, and keeps trying guesses over and over again, forever. You write this program, you hit run, you go for a cup of coffee, and the cool thing that happens is when you come back, the program spits out that there is precisely one correct thing to put into that box. So, what is that one thing? So the answer will be something to do with the projective cube. So, just a definition. Projective cube is generated by some numbers. So projective cube generated by numbers A1 up to AD. So a d-dimensional projective cube is just the set of all possible subset sums of these d numbers. So I don't want the empty set, but otherwise I take all possible subset sums. And if there are d generators, then I call this a d-dimensional projective cube. For example, sure triple is just two numbers and their subset sum. So it's just a T cube. And this thing that we tried here that didn't work was actually a 3 cube. Three-dimensional projective cube generated by X, Y, and Z. Now you might be wondering, why am I defining projective cubes if we have already seen that 3 cubes don't work? And well, the answer is, the correct analog of a 3 chain is not a 3 cube, but a 4 cube. So that's the theorem that we proved with Jason Long, is that in Z2 to the n, the largest 4 cube free set is L1 union L2. And in general, the analog of a K chain is not a K-dimensional projective cube, but rather a 2 to the K-dimensional projective cube. Right. So it's nice that these projective cubes appear here, because they're notorious for appearing all over additive combinatorics. They date back to Hilbert's, and there's also Lem's result by Folkman. They also appear in, for example, semi-radius proof or arithmetic progressions. So they have a long history. It's always nice when they just pop up randomly, unexpectedly. Let's just do a sanity check. Why are these two theorems even plausible? Why is it the case that the first two layers do not contain the 4-dimensional projective cube? Well, let's suppose that the first two layers do contain a 4-dimensional projective cube. That means they contain 4 numbers and all their possible subset sums. But if you think back of your first ever combinatorics class that you've taken when you were at this time, 20 years ago or something, one of the first examples of the pigeonhole principle we learned is that amongst 4 numbers, you always have a subset sum that's divisible by 4. So if the first two layers contain a 4-dimensional projective cube, then you got the 4 numbers generating this projective cube. You have a subset sum that's divisible by 4, but the first two layers are precisely those numbers that are not divisible by 4. So that's why first two layers are 4 cube free, and similarly, first k layers are 2 to the k cube free. So that's why these theorems are at least plausible. Alright, so instead of giving you the proof, I want to take a slightly different direction now, because there's a very natural question here that you have to ask if you're at this point. Namely, if you look at your dictionary now, so far we have written down that 2 chains correspond to 2 cubes, or short triples. We've written down that 3 chains correspond to 4-dimensional projective cubes, and so on, powers of 2. But there's a natural gap here. What happens with 3 cubes? What is the corresponding thing in the Boolean lattice? There is nothing between chain of length 2 and chain of length t. So in particular, what is the largest 3 cube 3 or z cube 3 subset of z2 to the n? We know the answer when d is a power of 2, but what if d is not a power of 2? So that's the natural question you want to ask in this point. And let me tell you what we think the answer is. So if you play around with it by hand or by computer, you will come up eventually with the following constructions. So I will denote by CD the best construction that avoids a d-dimensional projective cube. So if d is 2, you want to avoid a 2 cube, best thing you can do is take the first layer. If d is 4, best thing you can do is take the first 2 layers. For 3, the best construction seems to be to take the first layer, skip the second layer, take the third layer. So first and third layer. For 5, you take first 2 layers, skip 1, take the third one. 6, you take the first 2, skip 1, take 1, skip 1, take 1, and so on. 8, we know it's the first 3 layers, and so on. You can guess that there's a recursion here that I will tell you about in a second, but that's what best constructions seem to be. So what is this recursion that even gives these constructions? So let me show you this recursion for 26 that gives this construction. So you start with the number 26. You find the largest power of 2 that's not bigger than 26. It's 16. You write down 15. You subtract it, you get 11. And you write down 15 in binary, which is just 1, 1, 1, 1. And then you put a 0. And then you repeat the same thing with 11. Find the largest power of 2 is 8. So you write down 7, subtract, get 4. And you write down 7 in binary, you get 1, 1, 1. And you put a 0. And repeat. 4, largest power of 2 that's not bigger than 4 is 3. Subtract 3, you get 1. You write down 3 in binary, and you stop when you reach 1. So in particular, this tells us that C26, the best construction that avoids a 26-dimensional projective cube, seems to be take the first 4 layers, skip 1 layer, take the next 2 layers, skip 1 layer, and take the next 2 layers. So we cannot prove that these constructions are the best possible. What we could prove is that if you only look at constructions that are unions of layers, then these constructions are indeed best possible. But we cannot prove that the best construction is a union of layers. So, just a couple of words about the proof of this theorem. So of course you have to prove 2 things. You need to prove that, of course, these constructions don't contain a d-dimensional projective cube. And then we have to prove that anything larger than this does contain a d-dimensional projective cube. So of course, usually it's the case that proving that these constructions D-cube-free is very easy, and the hard part is showing that anything larger does contain a d-dimensional projective cube. But in this case, it's actually the complete opposite of what's happening. Proving that anything larger in these constructions does contain a d-dimensional projective cube is very easy. You can actually write down an explicit algorithm to find such a cube. The very, very difficult part for us was showing that these constructions do not contain a d-dimensional projective cube. So let me just illustrate to you what the difficulty is. Let's try together to prove that this construction doesn't contain a 26 cube.
Wait.
Yeah.
What is in this table? This you have proven is the best.
Best constructions amongst constructions that are unions of layers. But the hard direction is proving that this doesn't contain a d-dimensional projective cube, or in this case, a 26 cube. So how do we prove this? Oh, let's suppose someone comes along and tells us that they found a 26 cube lying inside of this set. Let's assume, moreover, so suppose there exists a 26 cube. So this 26 cube is generated by 26 numbers. So suppose this person is so nice that they tell us how many of the generators lie in each of these 3 blocks. So let's call this the first block, second block, and third block. So suppose that this person or fairy tells us that we have exactly 16 generators in B1, let's say 7 in B2, and the remainder, which is 3 in B3. Our goal is to show that this is impossible. But luckily for us, in this case, it's very easy actually. Because let's look at these 16 generators. Among 16 numbers, we have a subset sum that's divisible by 16. But B1 contains precisely those numbers that are not divisible by 16, which means amongst these 16 generators, there has to be a subset sum that lies in either B2 or B3. So we can carry one subset over, and from now on we will think of this subset as a new generator. So we get plus 1 here. And now we repeat. Amongst 8 numbers, there is a subset sum that's divisible by 8. So we can carry 1 over, because the subset sum has to be to the right of B2, so it has to be in B3. You end up with 4 generators in B3. But once you have 4 numbers in B3, the subset sum is divisible by 4 times their greatest common divisor, which means it has to be to the right of B3, which is impossible. So this case was very easy. The difficult part is if they tell us that now we have 17 generators in B1, let's say 6 in B2, and 3 in B3. So what is the problem? It's still true that if you have 17 numbers, you can find 2 subsets whose sum is divisible by 16. You could look at these 2 subsets, let's say they both lie in B2, you could carry them over. The problem is that if these 2 subsets intersect, it's not clear why their sum would need to be in your construction. So their sum is not an element of the projective cube anymore. There is no reason to assume that it have to be in our set. So this proof only works if these 2 subsets we'll find amongst the 17 numbers are disjoint. So we need a statement like this, that we need to prove that amongst 17 numbers we can find 2 disjoint sets whose sum is divisible by 16. So this is what we would have to prove. The problem with that statement is that it's just completely false. Because if someone gives me 17 copies of the number 1, so I'm never going to find two different subsets of these ones that are both sum to 0 more 16. The good thing is that if the projective cube does contain, is generated by 17 copies of the number 1, then one of the sums is 16, but 16 lies in layer 5. And that's exactly the layer that we skipped here. So this is what we haven't used yet, and we have to make use of it. So actually, the theorem that we will prove, if you have 17 numbers, you either have these two disjoint subset sums that are divisible by 16, or you have a sum that falls into this hole between blocks 1 and 2. And that's the theorem that we prove. So if you have 2 to the k plus x numbers, then at least one of two things holds. So at least one of the following two statements holds. First option, we find disjoint sums, and our whole proof works in the same way with the stereoscopic keep replacing subsets and disjoint generators kind of thing. So we can either find x plus 1 disjoint sums that are divisible by 2 to the k, or we can find at least one sum that falls into this hole after the block. So this is a subset sum that's congruent to 2 to the k mod 2 to the k plus 1. So if you plug in x equals 0 in here, you just get a normal pigeonhole result for 2 to the k. Actually, the way we prove this is a 10-page proof using downward induction. So in our proof, the hardest case was x equals 1. And the only way I know how to prove the statement for x equals 1 is to prove it for all larger x first. But it seems like a very natural statement that should have a very simple proof, but we only know a really long brute force proof of this statement. Right. So I'm running out of time, so I'm not going to be talking about the analogs of Kleitman's and Samotij's results. They are mostly open. In the last 1 minute, I just want to again mention one open problem that I already implicitly mentioned this talk, that is my personal favorite open problem in this area, is the case of a 3 cube. So I already told you that in case of 3 cube, in this picture you've seen that the best thing seems to be to take first and third layer. We don't know how to prove this. So conjecture, if you have a subset of z 2 to the n and doesn't contain a 3 cube, then the size of S is not bigger than the size of the first and third layer, which is 5/8 density. This is open. So this would be sharp because first and third layer is an example. You can start proving some upper bounds. So S at most 2/3 density is very easy, just by some very simple averaging argument. And actually, you can just prove this conjecture for some values of m using computer. N equals 8 is true. And using this, you can put this into your averaging argument, and you can actually prove that S is at most 5/8 plus 2 to the minus 10 or 11 times 2 to the n. So you can get arbitrary flows by just verifying large cases if I'm using computer. But this computer approach will never give you 5/8. This is my favorite open question in this area, and with that, I'd like to thank you and thank you for listening.